Hello, Year 10. Hope you had a lovely Easter break. And now I'm afraid, yes, we're back into Mr. Mumford's videos. I know you love them. You've been missing them over Easter, haven't you? Anyway, what we're moving to after Easter is we're moving into pressure. Part of that, we're now going to look at a bit more liquid pressure, and then we build up to atmospheric pressure. And look what we're looking at the end of last term was problems like this. Now, a starter for you, what I would do personally is I'll stop the video now, pause it, and I would then try and answer it myself, and then start the video again, and I'll show you what the answers are. Anyway, first of all here, you've got a hydraulic system, force acting down here 100 newtons on area A of 2 centimeters squared. The liquid then gets pushed all the way along here, and then it forces this one up. So that's where you're basically putting your force down. There's going to be the load. And this one has got an area 10 centimeters squared. And it asks, first of all, calculate the pressure in X. Now, using our formula working answer units, is first of all, the formula is equal to pressure divided by area. Okay, pressure equals force divided by area even. Therefore, the force acting down is going to be 100, and you divide it by 2. Therefore, the pressure in X is going to be 50 newtons per centimeter squared. Now, yes, you should use Newton per meter squared, but this is the legitimate units to use, and because that's in centimeter squared, that's fine. And then says, what's the pressure going to be in Y? Well, the pressure in Y is going to be exactly the same because it's the same liquid connecting the two chambers together. So it'll be 50 newtons per centimeter squared. It then calculates the force acting on the load, which is going to be here. You rearrange the equation. Force equals pressure multiplied by area. Therefore, you take your pressure, which is going to be 50 newtons per centimeter squared. As long as you keep the area in centimeters squared, you're going to be fine. And bingo, the answer pops out as 500 newtons. Now, like I said before, is if you look very carefully, isn't the area going to be 5 times bigger? Therefore, isn't the force going to be 5 times bigger? Which is a quick way to do it. And then said, which piston moves the bigger distance? Well, you're going to find this one will, because if you think about it, the cross-sectional area, that is going to have to go down a further distance to move the same volume of water. Water, liquid, whatever is there, move it across. And therefore, the piston, X, is going to be a bigger distance. Is this a force magnifier or distance magnifier? It's going to be a force magnifier because you made the force bigger. So, what this little video is all about is pressure in fluids and basically and depth. So what I mean by this is what you're going to have to do is calculate the pressure in columns of liquid at different depths. Then you state why pressure increases with depth. And these two here we're going to look at in a separate video. I'm just going to do this one and this one just now. Now, a demonstration you can do with this is all to do with looking at a can and go back. I can't remember where the simulation goes actually. I'll click on it and see what happens. This is called the can demonstration. And what you do is you have a can. And this is refusing to open up. Let's see where it takes me. If it does actually go there. No, it is not. And what you're doing is you'll I'll come back to a second. Go here. And you put water in here in the can. And then you've got hole here, here, and here. Now this one is going to squirt the water out here. This squirts out the water there, and this squirts out the water here if you have 3 holes. And it's pretty obvious looking at this. In fact, the pressure here, it must be greater than the pressure there because it's forcing it out with a bigger force because it goes a bigger distance from the base over here. And this shows nicely that pressure increases with depth. Now, another way of doing it is this cool little video, which I've got just over here. Here we go. Now, what you've got here is a diver, and he's got a bottle with air in it. And what he's going to do, he's going to go down deeper and deeper in the water. You see the bottom is crushed. That's because the outside pressure is bigger, 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 because pressure increases depth. And it's also why if you go very deep in the water, you find it harder to hold your breath when you go deep in the water, because there's a greater pressure in your lungs. Now, if you go back up again, this camera's trying to catch it up. Luckily, you start to see the bottle. Push this bottle up. It should get bigger and bigger and bigger because the pressure now decrease and go higher up. Now the bottle's going back to its original size. A really cool little demonstration that. Get rid of that video. Don't want that one anymore. So to go with that, then this is why dams are thick at the bottom, because these arrows here are showing the pressure or the force, and you can see here the arrows get bigger and bigger and bigger because pressure increases with depth. If you've got a diver, pressure is acting in all different directions because a diver is at the same depth here. Ooh, dizzy there. Because the diver is at the same depth, therefore the arrows are all the same size. But this crab further down the ocean is under extreme pressure. Now, there is an equation to work this out, and this equation, I've got it just about, getting hold of it, going to be here. Now, this simulation is really cool to show it to you. So what I've got here is I've got a super duper pressure sensor, which records the pressure in the liquid. Now it's in kilopascals, and that simply means 110,000. Well, here 110. The 1 kilopascal is 1,000 pascals, or newtons per meter squared. So basically, that all these numbers here are multiplied by 1,000. Now, what I've got here is a way of actually putting liquid into the water, and you can see as the depth increases, or the column height of water increases, you see the pressure increases. And I let the water out again, you can see the pressure then decreases. Hence, pressure increases with depth. Therefore, to work out the pressure at a certain depth, height must be involved in the equation. Well, there's something else involved as well. Now, what I've got here is I've got water which got a density of 1,000 kilograms per meter cubed. Now, if you really wanted to have a whole tub full of honey, if I suddenly now increase the density going up to honey, you see now the pressure has increased. That's because the density of the liquid also affects the pressure. So that's got to be in the equation. Now, there's one more thing as well that goes into it, is going to be gravity. Now, here on Earth, gravity is 9.81, and in your GCSE exam, they actually take it as 10. If I now increase the gravity going to Jupiter, you see again the pressure's increased, and that's because that makes the water depth. So the water is heavier, therefore there's a greater force acting down. So again, gravity comes into the equation as well. And to show you another unit of this is also, we can also measure in atmospheres. And 1 atmosphere is roughly about 1 kilopascals. It's 101,000. Because look what happens if I suddenly take the atmospheric pressure off. You can see it drops down. And this is another thing you've got to take into account, is actually atmosphere. We're going to look at next lesson. That creates additional pressure of the weight of the air above us. Therefore, you take atmosphere off, the pressure goes down, put the atmosphere on, it goes up again. And that's a very important thing to take into account. So, going back to here, this equation is where pressure is going to be the height multiplied by gravity multiplied by density. And you'll be glad to know this equation is actually given to you in the exam. Now, pressure, what we do is measure that in newtons per meter squared. The height is measured in meters. Gravity is measured in it's going to be in newtons per kilogram. And density is measured in kilograms per meter cubed. And here is an example sort of question you have to do. What's the pressure of a diver experienced at a depth of 10 meters and 16 meters in a diving tank? And here's the density of water as 1,000 kilograms per meter. Now I'll do one for you. You can do the other one. The pressure, oops, I don't know why I wrote down H there. Try again. The pressure is going to be H multiplied by G multiplied by rho. Therefore, the height is going to be, in this one, 10. I'm going to take gravity as 10, and then the density is going to be 1,000. So therefore, in my book, that's going to be 1, 2, 3, 4, 5. Okay, and the unit's going to be newtons per meter squared, which comes out here, and that's basically going back to my equation here in the units. Now, on the next one, 16 meters is dead easy to work out. Pressure equals height times G times rho, and then that's going to be 16 multiplied by 10, and now you're going to have 1,000 pops in here again, and that's going to be 161, and here goes through 1, 2, 3, 4. Now beforehand here is got your 16, then multiply it all the way through. Okay, and then you got 1, 2, 3, 4. Now that then, put it in standard form, that's going to be 1, 2, 3, 4, 5, 1.0 times 10 to the power 5. And this one, 1, 2, 3, 4, 5, is 1.6 times 10 to the power 5 newtons per meter squared. Hence pressure increases with depth. I'm going to put another little video on about diving onto the lesson. You can watch it later on. Okay, hope that all made sense.